We're working through substitutions. What's nice about this week is we are learning something new, but then we're reinforcing what we already know. So, for example, the take home and the test feature linear equations. Bernoulli equations, the first step is to identify them as Bernoulli, and then the second step is to turn them into linear equations. So let's kind of review that, and then we'll do one last example here with the logistic function, and then we'll move on to homogeneous equations. But remember, linear equations, you can write them in the form y prime plus p of xy is f of x. And the way you solve these is with our integrating factor.
Are you sharing your board?
Am I sharing your screen? Still shows. Oh, I'm sorry. Thank you. Thank you. Let's. We gotta share screen one. There we go. Okay. Thank you. All right. And Ryan popped in, so welcome in, Ryan. Okay. Now we're good. Okay, so linear equations, we solve them using integrating factor. By the way, integrating factors come back next week in a more general format. But the reason they're called integrating factors is they're called factors because you multiply through by them. And they're called integrating factors because they turn the left-hand side here into an exact differential, which you can then integrate. And then you're on your way. Okay. And I've been really happy that a couple people have been working through problems. They're like, look, I'm taking the derivative. I'm not quite getting the left-hand side, so I know I messed something up with the integrating factor. So that, that makes me feel good that you're checking things as you go. All right. So yesterday we talked about Bernoulli. Bernoulli looks like it starts off being, oh yeah, that's linear. Except on this side, instead of just having an f of x, you've got y to some power r. And what we showed yesterday is that if you divide through by that power of y, you can make a substitution and end up getting a linear equation in terms of u, which then you can back out to get y. Okay? So let's revisit the logistic equation. So last week we went through the derivation of the logistic equation. I think it was last Wednesday. Wednesday or last Tuesday, something like that. And the logistic equation, remember the sort of the basic idea is that the rate of growth of something is directly proportional to how much is there and how much room there is to grow. So the L was that limiting amount. And so that gave us the diffie q, p prime equals kp times L minus p. And then we made these assumptions. We assumed that k and L were bigger than 0, and that the initial amount p was always between 0 and L. All right. So last week we showed this was a separable equation. It wasn't linear, it was separable. So today we're going to say that, well, it still isn't linear, but it is Bernoulli. And we'll solve it using the Bernoulli process. And then we'll get the answer that way. Okay, so to show it's Bernoulli, I need to do a little bit of algebra here. We need to multiply this through. So KLP minus KP squared. Then I can subtract over here. And remember, for us, for Bernoulli, when we're thinking of y as a function of x, we're looking for y prime plus p of x y equals f of x y to the r power. Here, the dependent variable is p, the independent variable is t. So we got our, instead of y prime, we got our p prime. And instead of having something times y, we've got something times p to the first power. And then I move everything else to the other side. I've got something times a power of p. So sure enough, that's a Bernoulli. Okay. Are there any questions how this proves that the equation is Bernoulli? Do you see how we just move the letters around or reassign the letters? So since it's Bernoulli, we can start. What's our first step here for Bernoulli? We divide through by that power, in this case the power of y, the power of the dependent variable. So in this case I'm going to divide everything through by what? Yep, the p squared. So divide both sides by the p squared. So I'm going to get a p to the minus 2 p prime minus KL. And what do I get when I take p divided by p squared? P to the minus 1 equals, and then I just get the minus k over here. And now it's time for our substitution. So we're always going to let u, in this case, be p to the minus 1. And so, courtesy of the chain rule, u prime is going to be the derivative of something to the minus 1 power is minus 1 times that thing to the minus 2 power times the derivative of that thing. And as always, we're going to get the meat of that's going to be in the first term there. I just need to move that negative over. And so now in the land of u, p to the minus 2 p prime is minus u prime minus KL. Instead of p to the minus 1, that's u, and that's equal to minus k. And so if I multiply through by that negative 1, you get that. And now this is linear in u. It's all set for the integrating factor. All right, so what's our integrating factor going to be? Now, and this is something I've had some back and forth. I've had some good questions on the take-home, which I love it. I love that you're working on that. Remember, your integrating factor is going to be a function of whatever the independent variable is. So back when we did, the logistic equation, the dependent variable was p, the independent variable was t. So the integrating factor should be a function of t to be consistent, all right? And that's going to be e to the integral of what? So what am I integrating here in the exponent? KL. And k and l are both constants. So when you integrate k times l, you're going to get what? KLT. All right, which sounds like a sandwich. And once again, we suppress the constant of integration here because adding a constant in the exponent is just tantamount to multiplying by a positive number, and multiplying an equation by a positive number doesn't help with solving the equation. All right. So now we're going to multiply this through here, e to the k lt u prime plus kl e to the k lt u is equal to k e to the k lt. And the left-hand side, sure enough, is the exact differential, e to the k lt u, and that's e to the k, k e to the k lt. And I'm going to double check something I didn't forget. Yeah, that all looks good. Sometimes when I recopy things from one slide to the next, I lose things. It's just been particularly bad this week. But I think I got everything. This is freezing on me now, which isn't good. All right. So far, so good. All right, so now I'm going to integrate both sides. Once again, the independent variable here is t, so integrate with respect to t. And I will get e to the klt u equals, and then when you integrate this, what's going to happen? I'm integrating with respect to t. The k and the l are constants. We're assuming k and l are both positive. So when I integrate e to the klt, what's going to happen? I'm going to have that k times what? I'm going to have e to the klt, but I'd have to divide by what? K and L plus C. So the K's will cancel. And I got e to the KLTU equals 1 over L e to the KLT plus C. And now we can substitute back in for the U. U was p to the minus 1 power. So I got e to the KLT p to the minus 1 is equal to 1 over L e to the KLT plus C. And at this point, we can impose the initial condition if we want. So p at 0 is p naught. And then we can carry that along and see how we can rewrite that if we need to. But when I plug in t equals 0, what's going to happen to all the e's? So e to the KLT, when t is 0, those are all going to be what? Yeah, those are going to all be 1. So I'm going to have p naught to the minus 1 equals 1 over L plus C. So C is going to be 1 over p naught minus 1 over L. Which I guess we could get a common denominator there. So we would get the C, and we'll see if there's a better way to write that later on. But then we can solve for P. So e to the KLT, p to the minus 1 equals 1 over L e to the KLT plus C. So I can, if I want to solve for P now, I can divide through by that exponential. And once again, when you divide by e to the KLT, That's the same as multiplying by e to the what? Negative KLT. Very good. And now p to the minus 1, that's 1 over p. That doesn't mean the inverse of p. So once again, the context is important here. That's an algebraic power, not a functional operation. So let's see. We're going to have to flip this over to get this to work out. So it all depends on how you want to proceed here. We could get a common denominator first and then flip it. I mean, we could do that. Let's do that. What would be the common denominator here? LP naught, and then we would have P naught plus L minus P naught, and I could put e to the KLT down here. Whoop. So if I want to add these two, we'd have to have a P naught e to the minus, yeah, if we're going to do that, yeah, we should put this here, right? So this would be, if we're going to do L P naught e to the KLT, then this is missing a P naught, right? E to the KLT? Yeah. Then I can flip it over. And I would have L P naught e to the KLT over L minus P naught plus P naught e to the KLT. And then I could go through, it looks like let's see. I'm trying to get this to look like what we had before with our C. So I think we could divide, I think our C last time, yeah, if we divide through by P naught, so if we divide top and bottom by P naught, this is what we would get. P equals, so the numerator by P naught would be L e to the KLT divided by, and then this would be L minus P naught over P naught, which I think was our original C from the first time we solved this, plus e to the KLT. And you can go back last week and check this. I think this is what we had for C the first time, because it's a ratio of how much is the room to grow over the initial amount. Or this might have been flipped and multiplied there. I'm not sure. But this is essentially the same equation we had before. You might need to do some algebra to move things around. But you get the same solution. Okay? So it's up to you. I mean, I think anytime you can make things linear, I think they're easier to solve because it's a more direct method. There's certainly a lot less algebra involved than when we separated variables, because if you recall, when we separated variables, we had to resolve things into partial fractions, and we had to integrate, then we had to do some log properties to get the logs by themselves, then we had to exponentiate, then we had to solve for p. This was a more direct method to get us to the same place. All right, and you'll see that on the next take home. Is it the next one or the one after that? But there's going to be different ways to solve. Like I think the one you're working on for tomorrow, you've got an equation that is not linear in y, but it is separable. And then you find out it is linear in x. So for any given differential equation, it's worth taking some time to investigate what all types it is. Because one solution methodology might be easier than another. Okay, so that's it for Bernoulli's. And here's some extra practice on that. All right. So now we're going to talk about another type of substitution that's for these types of equations. Okay. Now let's talk about this word. We already used this word in the context of linear equations. So when we talked about a homogeneous linear equation is a linear equation where the f of x is equal to 0. So homogeneous linear means this. And when we move into chapter 5 and we get to the higher order linear, this is what homogeneous is going to mean. Homogeneous means it's a solution to 0. And if you're in the linear algebra, a homogeneous system of equations is going to be a system of equations that's equal to 0. Okay. Now there is another use of this adjective here in differential equations. It's spelled the same way, but I like to be a little facetious with it. So to distinguish what we're going to talk about today from what we already talked about, I'm going to pronounce this homogeneous. It's the same word, I'm just pronouncing it differently. Homogeneous. Now, when you see something like homogeneous, like in chemistry or something, like a homogeneous solution, or homogeneous mixture or something, this means that something is equally distributed. Right? So like, when you're like baking or something and you put a couple of ingredients together, you stir up the dry ingredients to evenly distribute them before you add in your eggs or whatever. Okay? So equally distributed. And so we got the following definition. A function f of xy is said to be homogeneous of degree n if f of tx comma ty equals t to the n f of xy. So what this is saying is a homogeneous function, the powers are equally distributed. So if you scale x and scale y by the same factor, the result is scaling the whole function by that factor to the nth power. That's homogeneous of degree n. Okay? So think of it as the powers are equally distributed. So as an example, if I look at this function here, if I look at f of tx ty, everywhere I see an x, I'm going to put parentheses around it, replace it with tx ty. Whoops. So we can see what happens here. I'm going to get my 4xy squared, and I'm going to get a factor of t here and two factors of t there. That's going to give me a t cubed. This is going to give me a t cubed x cubed minus 2 t cubed x squared y. And now I notice that each of these terms has a t cubed in it. So I could factor that t cubed out and get 4xy squared plus x cubed minus 2x squared y. And sure enough, this is exactly my f of xy. Right? So in this particular case, we've shown f of tx ty is t cubed f of xy. And so this function is homogeneous of degree 3. That essentially means all of the terms, if you look at the degree of all the terms, they're all 3. So if you add up the exponents in each term, notice they're all what? 3. This is just a way of codifying it. Okay? That's just a way of codifying that. Now, if I look at this one, if I just slightly alter it a little bit, you'll notice that this term has degree what? 2, so there'd only be a t squared you can pull out of him, whereas all these other ones are degree what? 3, so this will not be homogeneous. Okay. Let's take a look at this next one here, because this is the one that we're going to be focusing on in this course. This type of homogeneity here. If you put in tx, ty to this one, you notice in the numerator you can factor out a t to the what? We're going to get a t squared up there. And down here I'm going to also get a what? T squared you can cancel out. So here the t's from the numerator completely cancel out the t's from the denominator. And so if I wanted to, I could say, well, this is homogeneous of degree 0, meaning that f of tx ty equals t to the 0 f of xy, or I can think of t to the 0 being 1. There it is. So if you scale x and y by the same factor, it doesn't do anything to the function. So as long as you scale x and y the exact same amount, the function doesn't change. So you can think geometrically what that means. That's an interesting thing to think about geometrically, about what it means for the graphs of these things. So Desmos 3D would be fun here. So Desmos 3D would be fun. Kind of graph this function and try to see if you can, what does this property mean geometrically? So our focus here in differential equations are going to be on functions that are homogeneous of degree 0. So suppose f is homogeneous with of degree 0, then that means that f of tx ty is the same as f of xy. So here's what that means. We can rewrite f of xy this way. We can rewrite it as f of x times 1 over x, comma x times y over x. And then I can think of this as being the scaling factor t. Excuse me, it's x times 1. What I'm doing here. There you go. Whoops. This is x times 1 times x times y over x. So if I think of this is now like my scaling factor, so I can factor that out. So that would be x to the 0 f of 1 y over x. In other words, f of 1 comma y over x. So what's the point of doing this? This says that if I let u be y over x, a function that's homogeneous, I'm just scaling the first component. I'm just scaling this I'm basically rewriting this. I'm thinking of x as the scaling factor. So I'm rewriting x as a t and just having 1 there. So I'm scaling the x component and y component by x. I'm just rewriting it so that x is the scaling factor. And then bringing it out. So this property says, this is, we can put a's and b's in here if you want, if this helps. This means if no matter what you multiply by, as long as you multiply the first and second input by the same number, you're going to get the same thing out. So here I'm thinking of this. I'm thinking of this as multiplying the first and second input by x. If the first input is 1 and the second is y over x. Yeah. Yeah, it's a little sleight of hand. All these substitutions are kind of like little magic tricks, right? Like the Bernoulli. Now all of a sudden things are going to get good. But basically what this means is that if this is homogeneous of degree 0, then we can make a substitution, u equals y over x. And what that'll do is that'll change my function, which now looks, depends upon two variables. I can recast it as a function of u, where u is y over x. So why would we want to do such a thing? Well, now it's time to define homogeneous differential equation. So this is a new definition here. So homogeneous first order differential equation. All right, so this is the nonlinear version of that. You've got y prime equals f of x, y. So this is the same kind of setup we had to check Picard's theorem, where this is a function, this is homogeneous of degree 0. All right, so that's what a homogeneous first order differential equation is. This is degree 0. And what happens is, if I let u be y over x, the claim is that when I do this substitution, this is going to always result in a separable equation. So if you have a nonlinear equation and you find that it's not separable, if you write it into this standard form and you notice that the function is homogeneous of degree 0, then you can change this into a separable equation. So just like Bernoulli takes a nonlinear and turns it into a linear, homogeneous substitution takes something that's not separable and makes it separable. So what we'll do, I think the best way to do this is go through an example here. And then we'll show that it works all the time. So just to kind of talk about this substitution here, here's our f of xy is 6xy over x squared plus y squared. If we make the substitution, u equals y over x, we can also think of this as letting y equals u times x. And so let's see what happens if I substitute that in. F of x comma ux. Because of the homogeneity, the x's should all cancel out. So this would be 6x times ux over x squared plus ux squared. And so just like the t did before, here I've got x squared. I can factor out of both numerator and denominator. So that'll cancel out. And so this is equal to f of 1 comma u. So if I go back to my original and plug in 1 for x and u for y, that's exactly what I've got there. And so that's what we're calling capital F of u. So do you see how this substitution takes this function of two variables into a function of one, and why it's working here? This might help clear stuff up. Yeah. All right, so the claim is, in general, this is going to take an equation that's not separable and make it separable. So I think with the time left, we should be able to solve this one and then Tomorrow we'll pick up and prove that this method works in general. But let's take a look at this example here. We got y prime is y squared minus x squared over 2xy minus x squared. And you can almost tell by looking at it, this is going to be homogeneous of degree 0, because look at the degree of each of these terms. So, yeah, they're all 2. So in the numerator, I'd be factoring out a t squared. In the denominator, I'd be factoring out a t squared. And so those t squares would cancel out. Okay. So if you wanted to be, to write all this down, you would identify the, you'd say, okay, well, I'm in the form y prime equals f of xy. You would identify the f of xy, and then you would go through f of tx ty, and then show that you just get f of xy back. So that's how you would actually establish that the differential equation is homogeneous. All right. But we've done a couple examples of this kind of algebra, so I don't think we need to go through that. So the substitution is we're going to let u be y over x, or once again, y equals ux. I think it'll say explain why the differential equation is homogeneous. So then you would go through and do that. You can either do it formally with the t's, or you could just write down a sentence or two about the degrees of the terms. But yeah, because a lot of it is being able to recognize what kind of diffie-q it is. So, yeah, but if it, yeah. Okay, so now we need to figure out how the derivative is going to work, because, so when I go to take the derivative here, y prime, what rule am I going to have to use if I take the derivative of this with respect to x? So y prime would be the derivative of this with respect to x. So what rule do I have to use here? Yeah, your product rule. So derivative of the first times the second plus the first times the derivative of the second, but the derivative of x is just what? 1. So here's the, that's what we plug in for the y prime. All right. So going back to the diffie-q, we've got y prime equals y squared minus x squared over 2xy minus x squared. Because of the squares, it's not going to be linear. You can try to rewrite it as a Bernoulli. You can try to separate variables. We're down to the last technique we have here. We're going to plug in the y prime. U prime x plus u is equal to, and now we're going to plug in ux for y. And sure enough, on the right-hand side, all of the x's are going to cancel out. That's how you know if things are working your way. All the x's on the right-hand side should cancel out, because it's supposed to be a function of degree 0. So you can see all that happening here. Thank you. 2u minus 1. Thank you. There we go. Okay. Now the claim is this is separable. So if it's separable, we should be able to get all the u's on one side and all the x's on the other. All right, so we've got some algebra to do. So the goal here for separable is I've got h of u, u prime, equal to some g of x. That's our goal, right? So we'll get the u prime on one side and then try to get all the u's with that and then all the x's on the other. So if I start off here, let's get the u prime. I got u prime x would be u squared minus 1 over 2u minus 1 minus u. And since we're going to be dividing stuff over, let's go ahead and get a common denominator there again. So we got to be careful here simplifying this, or else we'll get something we can't properly integrate. Well, I mean, we'd be able to integrate it, but it won't be nice. So when the dust settles in this numerator, what happens? I'm going to get a u squared minus a 2u squared. So that's going to be how many u squared in the numerator? Minus u squared. And then I got a minus u times a minus 1. That's going to give me a plus u. And then we still have the minus 1. And this is all divided by 2u minus 1. And so once again, my goal is to get all the u's on one side, all the x's on the other. So we want to get all the u's times u prime equal g of x. And sure enough, we can do that. We would just divide both sides by x and divide both sides by this fraction, which means I'd be flipping the fraction over. And so this shows that it's separable. All right, so to solve a separable equation, we separate and integrate. You write this in the differential form. And now that we've got differential form, we can integrate. How would you integrate the left-hand side of this? Yeah, you do. Yeah, you can't really. Yeah, I like that. Yeah, you do like a v substitution. All right. Or if you're like me and your v's and u's look too close together, you could do a w substitution. Right? Now, this is kind of like a pun because we've already done a u substitution earlier. So we'll do a double u. Get it? It's a bad joke. But the sun's out. So we'll tolerate bad jokes with the sun out. So the dw would be minus 2u plus 1 dw. So I can, this is exactly the opposite of what I have up here. So the left-hand side, if you go through the steps, you should get a negative natural log absolute value of this. Because you're off by a negative there in the dw. And then the right-hand side, you get that natural log. Yeah. Yeah. Well, technically it's w and not omega. But I like how your thinking is around. All right, so we get to there. We can move the negative over if we choose to. And now we can put the y's back in. like that. And then, did they ask for an explicit or implicit? So at this point, let's see what they asked. An implicit one parameter family of solutions. All right. So now technically we're done. However, you got logs on both sides. Let's sort of do a little more work here. We can use log properties to combine these. Addition on the outside turns into what on the inside? Multiplication. So that's the same as multiplying all these together. How do I get rid of the natural log? With ease. I'll call that C3. Since C3 is e to the something, C3 is always going to be a positive number. How can I get rid of the absolute values? Plus or minus. C3 is always positive, so I can call this C4, and then that's just not 0. And then if I want to get the x's out of the denominator, I can multiply through by x. So, yes, thank you. And then you could multiply everything through by a -1. And you could write it that way. This is a one parameter implicit family just as much as the other one is. You follow? So it's up to you. Now, this would be, how do you check your answer? This would be another one. This would be a great one. Check it by implicit differentiation, right? So you call this thing your f of x, y. I'll leave this to you, right? This is kind of the stuff you did on the first take home. If you call this f of x, y, then your y prime would be minus fx over fy. And you might have to solve for that c to help you with that, but you can show that it matches. All right, so let's see what we had here. Yeah, we had a minus cx plus cx. C's are c's. But there it is. Okay. So next time we will prove that this substitution works all the time. And then we'll go through an initial value problem. And that means Thursday will be a work day. So it'll be a day for you to tune in with answers. I'm also trying to get permission from the dean to have an extra online office hour. And I'd put that on Friday during class time. It occurred to me most of you probably have that time open anyway, and if you're one of these people that are taking physics and stuff, you should have, hopefully have that Friday open because you don't have physics on Friday. Okay. Have a great rest of your day, everyone, and we'll see you tomorrow.